stuff together, hasn't it? So what I'm going to be presenting today is a little bit of a look to the future. And to try to keep it from being a sales pitch, one of the things I wanted to do was to focus on the problems that need to be solved. And so just a quick update on carbon nanotube memory. It's essentially a resistive network that is switched into ones and zeros using the atomic interactions of carbon nanotubes within the substrate. It has no dielectrics. It's basically a standalone resistive memory type. What is it? It's essentially DRAM performance. It is DRAM endurance. It has no heat sensitivity. It scales. And I want to avoid using any magic references, but it's a pretty cool little memory. I think you'll be quite happy with it when you see this in your systems. But what problem is this going to solve for us? Well, there's a couple of problems. One is you have to think about what is the definition of persistence. And persistence, it means that when power fails, the data is going to be guaranteed. And we've looked a lot at, for example, what happens when you have a bus transaction. We saw a presentation today where the NVDIMM-N, you're going to take on power fail and back everything from the DRAM up to NAND Flash and then restore it after power is restored. We also saw another architecture where the contents were stored on the memory channel and had to be moved across the memory bus over to another module for the backup. And so the definition of persistence changes. The amount of energy that you need to supply is going to be very different based on what architecture you apply. So that is the problem that we want to solve. So a couple of solutions here. One is to make a high-density cross-point architecture, which is essentially a main memory that is inherently non-volatile. The other part of the solution is carbon nanotube memory can be put into a 1T, 1R matrix for smaller arrays to be dropped down onto controllers, because the memory that's in the controller also has to be saved somewhere. So if you had a controller memory that was inherently non-volatile, power fail presents no risk to you and no latency on power fail for recovering your system. So it's like a DRAM minus the D, and I don't want to hear any D jokes. It is not dynamic in the sense that it's a random access memory, byte addressable, and fully deterministic. It looks just like a DDR4 device, but it doesn't require refresh. It has no fifth activation penalties. It has no long and short types of group access penalties. It acts like a very high efficiency memory device. So if we compare this to an NVDIMM, and again, this is the problem that we want to solve. What you have with today's NVDIMMs is you kind of take a big performance penalty in the sense that if you have to cut your memory capacity in half in order to have room on the DIMM for the flash memory that's going to do the backup. And so that's made it a little bit of a tough sell, in that if you were able to get say a 64 gigabyte DRAM module, or you can get 32 gigabytes plus persistence, it's a little bit harder sell than if you had a 64 gigabyte memory module to begin with. The other thing is the complex save and restore cycle, and that the presence of that external battery or supercapacitor for the energy source. And that is really part of the problem. Every minute that it takes to save and restore your contents on a power fail is another minute that system is not available for customers to be renting time on. So if you look at the NRAM implementation of the same module, instead of a complex controller that's copying data here and there, it's just an RDIMM or an LRDIMM. It's just a standard memory module, so it gets the full capacity of the memory module, and it inherently saves and restores without any interaction. So, for example, on the NVDIMM side, the problem is that on a power fail, you have to complete the burst that's in progress. You have to then save all pending operations out of your controller chip. You could have to copy the DRAM over to the non-volatile memory, like the flash. When power comes back on, you check your save status, you copy the non-volatile memory back to the DRAM, and you run. So we're literally talking about multiple farads of backup capacitance, and you're talking about multiple minutes of save and restore. As opposed to if you had a memory that was inherently non-volatile, you just have to complete the burst that's in progress, essentially 64 bytes of data, and then there's nothing. You just turn power off. When power comes back, you just run again. Also, if you look at the SSD class of devices, and so the SSD class of devices, the same kind of thing. You have to have a power supply with an energy store, and you have a flash array and a DRAM cache. In this context, what the DRAM cache is doing is it's doing like command reordering and all that other stuff. Well, when on power fail, you can't afford to lose that cache. So you have to keep the entire flash array powered up, controller powered up, the DRAM powered up while you do that copy. So the result of that is that the size of your cache is a function of how many capacitors you can fit on your SSD. Well, if you had an NRAM, you'd completely eliminate that. Now, not only do you have essentially no backup time needed for power fail, you also don't have to save space for all these silly capacitors. You can increase the amount of capacity that's on your memory module, and your cache can be any size you want it to be based on your performance models, not on your power models. So, summary, it combines the best features of a DRAM and an NVM. It's flexible, it's stackable, and it's a fundamental technology that can be applied at the component level, but also put on top of your existing controller devices, and completely eliminates the need for all of these complex power subsystems and timing. And quote a customer, have I mentioned to you how much I hate batteries? They said that 6 times in a 90-minute meeting. So,
yeah, hi. So you said at the beginning that it's not going to be a sales pitch. I think we kind of understand where you're going with this. I mean, we're actually waiting for the sales pitch. So where is this in terms of being an actual product out there?
Soon enough. Yeah, that's a discussion for offline, so I think we exchanged cards earlier.
Too tight on time.
Okay, thank you for your time.
Okay, my name is Andy Walker. I've got about 15 minutes to get through this, so I'll talk fast. I want to thank anybody who created this prestigious forum to allow me to talk to this. And I also notice we have the NRAM pioneers in the audience, so I want to thank them also for creating the ecosystem where this is all happening. My background is 30-odd years of silicon technology, Holland, United States. I came into NRAM about 1 year ago, and my eyes have been opened. STT has created some interesting technologies, which I hope will enhance the ecosystem, and I hope to persuade you about that. Okay? Okay, so I'm going to talk about the creaking pyramid, all about the existing memory technologies, where they are, what their challenges are becoming, what and where is NRAM, the state-of-the-art PMTJ. Many people are working on this, and it's an extremely interesting area. How we propose to unleash NRAM into that creaking pyramid to help the existing technologies survive, and then NRAM Unbound. So this is the what I put together. I've worked in most of these areas over the past 30-odd years. You can see here, this is the pyramid. We've got the SRAM caches close to the CPU. On chip with the CPU, we have a gap to DRAM. Everything above there is volatile. We have mind the gap here, then we have NAND, and we have disk speed enhancement going up, capacity increasing going down. And in the corner up there, we have NRAM. At the moment, at least at the major manufacturers, restricted to embedded non-volatile. The pioneers of NRAM are trying to get it into these gaps here, trying to take over a portion of DRAM. But at the moment, it's sort of limited. But an ecosystem is developing. So if you look at SRAM, for example, SRAM is a very interesting area. If you look at the SRAM cell area in S squared as a function of the CMOS technology node on a log scale, you can see going from planar CMOS to FinFET CMOS, the efficiency of SRAM is getting worse, the efficiency of layout. And that is combined with increasing amounts of SRAM being placed on chip. And we get problems with the amount of area being taken up, the cost, the power dissipation, and so on. So a real problem, a real challenge for SRAM here. Then for DRAM, this is a cross-section. What happens after 30 nanometer pitch? DRAM is reaching the limits of its scalability. What happens after 30 nanometers pitch? Is there any room left? Right? NAND has already taken the leap into the 3D area. So a very interesting leap into 3D NAND, very interesting technology there. But let me be clear, NRAM will probably not take over NAND. So in my experience, that's highly unlikely, despite what some people are saying. But I think NRAM has a capability of filling the gaps here, taking a portion of DRAM, and certainly taking over some cache replacement for SRAM, if certain things happen. So here are the challenges within the memory hierarchy summarized. SRAM, ever larger caches required, inefficient scaling of the FinFET CMOS for SRAM layout, large leakage currents dominating power dissipation, DRAM scalability reaching fundamental limits, refresh power dissipation only getting worse, and it is not monolithically 3D stackable, unlike NAND was or is. NAND, I won't talk too much about that because I don't think it's going to take over NAND. And then the gaps. Does 3D XPoint fill the gap, fit the bill for filling the gaps? Can RERAM really be made to work? And what else can fill the gaps? Okay, so what is MRAM? For those of you who don't know, it's basically a magnetic RERAM. So we have here, for example, a very simple cell, a transistor, a control transistor, select device, word line, bit line, source line, and this variable resistor, which is the MTJ, the magnetic tunnel junction. It's all about layers of a free layer, which can flip its magnetization, and a fixed layer, which is a fixed magnetization. And then between the two layers, we have a very thin magnesium oxide, which is a tunnel dielectric. The ease of tunneling through that layer is defined by the orientation, relative orientation of the magnetization vectors in the free layer and the fixed layer. So if they're anti-parallel, we get high resistance. If they're parallel, we get lower resistance. Now, the interesting thing for a memory guy is that writing is stochastic. So we can try to write that memory, but it is a probabilistic write method. So it may not write or it may write, but that function is mathematically described. The write error rate on a log scale as a function of the voltage or current through that device is very finely defined, and with the pulse width as a factor. So that means that mathematical description of the switch allows CMOS designers to take that and design circuitry around that. So I'll come more onto that. So that probabilistic nature is very, very important to realize. So where is MRAM? So like I said, it seems to be emerging as the embedded non-volatile memory of choice in advanced CMOS. It has lower voltage and fewer masks than traditional flash. Flash is reaching the limitations as regards cost and embeddability into advanced CMOS. It's stochastic. If you want to get low write error rates, you need to increase the voltage, increase the current through the device, but that leads to a wear-out mechanism in the thin oxide, so it reduces the endurance of the memory. Retention and endurance are strongly inversely linked. So retention requires a stiff magnetization vector in the free layer, but that means that high switching currents are needed, which increase the wear-out mechanism in that magnesium oxide, so limiting the endurance. So the question is MRAM confined to the embedded non-volatile cage? Okay, state-of-the-art MRAM. So retention and endurance and switching current are being engineered by various companies to see if they can get a handle on this, to see if it can break out of that non-volatile memory cage. And then Toshiba, for example, has done a ton of work on materials engineering to reduce the current required to switch and also increase the speed for switching. By scaling, you can do that, and also with magnetic materials engineering, you can do that. So they've been trying to push MRAM into the SRAM cache replacement area. And then scaling the soft magnet PMTJ allows lower switching currents, lower write power dissipation, high endurance, smaller bit cells with some level of persistence. But that's a tricky optimization to go down. There's always, after all these years, there's a conservation of misery in this area, because whenever you try to optimize one thing, something else falls apart, right? And MTJs, MRAM are especially prone to this conservation of misery. You try and optimize one thing, something else falls apart. So are we getting there? Are SRAM and DRAM really replaceable? Are the gaps fillable? What can be done to help unleash MRAM? So let me tell you a wee bit more. So my company, I joined last year, and having the experience in silicon was quite useful, because I could see where their special IP, their special developments could come in handy. The company has a unique facility, in-house facility, which is a back-end of line nanofab. So we can get CMOS wafers in, we can do our own MTJs, complete the process, and then test. And we can get to high densities, and this is very important because I'm leading a team to look at magnetic DRAM, storage class memory, persistent memory. And then we have unique magnetics. We have a polarizer, which is a layer or two, which can be added to anybody else's MTJ, and we get faster switching, lower write currents, which are critical for smaller dimensions. But what is uniquely fascinating for me when I first joined was this unique circuits. We have something called an endurance engine. So it is a piece of circuitry that is placed that understands the physics of the MTJ and can use that to boost endurance by up to 6 orders of magnitude by reducing the electrical stress on the MTJ. So that mathematical description of the switch allows the endurance engine to take hold. So, like I said, we have the engine, and this is what I believe is the SanDisk of MRAM, because it's an understanding of the physics of the switch, creating circuitry that allows a boost in performance reliability by orders of magnitude. And it can reduce switching currents, it enhances speed, and if somebody said to me a year ago that this company had a piece of circuitry that could be added to a non-volatile memory that could boost endurance by 6 orders, I would have said there's no way that can be done. But it can. So this is one of the reasons I joined the company. The polarizer, we've come up with some unusual materials that can boost performance. Magnetics, and we have a group working on a manufacturable DRAM replacement, magnetic DRAM, using manufacturable known materials for magnetic DRAM. So this is the physics of the engine. So remember that write error rate as a function, the stochastic nature of the switch as a function of the voltage, because it is well defined by a certain function, and also with the pulse, the faster pulse effect. We can take that, we can reduce the electrical stress in the device, and what that does is increase the write error rate. That increased write error rate is dealt with using the engine without any impact to speed or no extra ECC required. That reduction in electrical stress has an exponential impact on endurance because it reduces the stress across the thin magnesium oxide. So what it allows is reduced electrical stress, large increases in endurance of 5 to 6 orders of magnitude, and the engine deals with the resultant WER increase with transparent to the user. So this is an unusual piece of circuitry. It can actually lead, you would think, oh, we need to add stuff in the periphery of a memory, which would add cost and so on, but that can actually result in a smaller bit cell size, so the total footprint of the memory can actually be reduced as well. So it's a highly unusual piece of IP. And because the argument is we don't need to change any material properties, this is gaining traction with certain manufacturers because they've done all this engineering to create their MTJ. When we say we have a circuit that can be added to their process or their solution that can magnify their benefit by 6 orders of magnitude, it has serious implications. So how do we unleash MRAM? So what that does is that piece of circuitry and that polarizer allow reductions in switching current, allow endurance increases. It means that instead of 10 to the 8 cycles for the MTJ, we can take it to 10 to the 14 cycles, and suddenly you're in the realm of SRAM and DRAM replacement. And the reduction in current allows you to minimize the cell footprint as well. So suddenly you get a cost benefit in the bit cell size. So suddenly you're in the area of being able to replace SRAM for cache, embedded, also standalone SRAM, and there's a path to magnetic DRAM as well. So this is for the high density. We are looking at, we're starting out at this level here with embedded MRAM, 40 F squared cell size, 10 to the 6 to 10 to the 9 endurance. We are taking our engine, we are reducing the footprint of the cell, we're getting a reduction in cell size, and then with a proprietary approach for the selector, but a manufacturable selector that uses existing materials in manufacturing, we think we can get to these kind of levels, 10 to the 13 endurance, X where X is less than 10 or 9. And then also to get multi-bit. Multi-bit is difficult because the differences between the high resistance and low resistance are not that great, but we have certain ideas on how to boost that and how to be able to use that. And we have certain requirements, and our company has certain advantages in each area, but I'll leave you to look at that afterwards. So MRAM Unbound. So what do these things do? So the ecosystem is developing. The pioneers have done that already. We can work with anybody's MTJ from the pioneers or from the major manufacturers, and we can allow the MRAM to impinge upon and replace certain types of memory within the memory hierarchy. So you can see there, SRAM. Perhaps not the fastest cache, but certainly the level 2 and the last level cache are now in danger of being replaced by MRAM. The gap between DRAM and SRAM can also be replaced with a persistent DRAM solution, which is fast, not as fast as the last level cache, but in between the fastest DRAM and that level. We have the capability of taking over certain areas within the gap as well between DRAM and NAND. But again, NAND, I think, has its own issues, its own requirements, and its own interesting roadmap for the next 10 years. Okay? So that's it. Thank you very much.